Start recording. I always forget. Okay, so the topic for today is free induction decay. So what does that mean? So free means you're not turning on any extra fields. Induction means you did an RF pulse, and decay means we're now recording. So that just means, how does the signal evolve over time if you're not messing with it? And you just induced it and you just let it go. And so what we want to develop today is the idea of T2 versus T2 star. And this will introduce us to the idea of getting an echo. So what does it mean to get an echo? So when we talked last time about, let's just sort of review what we did so far. So we started off with the signal equation. We started off with the signal equation, and the signal equation basically was, how do we get from, this brain precession. So, protons in the brain that are precessing, how do we get from that to this signal over time? So that's the signal equation. And when we were talking about that, we kind of glossed over the phase-sensitive detection, and then we said, but here's how the phase-sensitive detection works. And the phase-sensitive detection was, we have one voltage coming out of that coil from all the sum of the precessing protons, and we turn it into this real and imaginary. So we have one set of data, and we multiply by the transmitter, and we get a real and imaginary, and that then gives us an actual vector that says, what direction and what strength the magnetic field vector summed across the brain is. So that was the phase-sensitive detection part. And so what are we talking about today? So what we're talking about today, FID, is now let's actually consider multiple frequencies. So if you came to the Friday graduate session, I was trying to say, don't pay attention to these multiple frequencies. Those are not. It's going to mess you up when you try to think about how the signal arises. But now we're going to actually just pay attention to them for a little bit to try to understand the difference between T2 and T2 star. So in order to understand that difference, we have to sort of consider multiple frequencies. And there's always multiple frequencies, because the magnetic field is never completely uniform across the brain. So there's always multiple frequencies. So we're going to talk about just an idealized equation for multiple frequencies that's much more simple than the actual reality of what the multiple frequencies are. But that's just the way that we work, we work in physics. Consider a spherical cow. Cows are not spherical, but for certain approximate calculations, a spherical cow is a good thing. So we're going to talk about sort of a simple equation for multiple frequencies. That's not too far off. And then try to see how this T2 star business versus T2 comes about. So if we're considering multiple frequencies, then we have to look at our signal. So here's our signal. So it's our complex valued signal, two-component number signal as a function of time. And so that's the signal that we record, but now we're going to consider consider the fact that that's actually the sum across multiple frequencies over time. So the very first part is we have the sine of the flip angle. So depending on how long you turn the RF on, you will get a certain amount of longitudinal magnetization. So remember, if you go in the magnet, you get magnetized after a couple T1 units of time, you're pretty much fully magnetized to the equilibrium magnetization, and so you're sort of magnetized in the Z direction, and you reach that equilibrium of magnetization. Then you do an RF pulse, and the RF pulse causes the amount of longitudinal magnetization to be reduced because you sort of have flipped the summed protons down, and they, start to have a smaller Z component. So the amount of that energy that you deposited into the system that causes some of the protons to sort of flip and get into the higher energy state that's kind of opposite the magnetic field, that's the flip angle. And so why is it the sine of the flip angle? Well, if you just look at, so if this is, or let me just draw it in a different color. So if this is the starting if that's the starting flip, and then this is what we flip to, and if we assume that the flip occurred very rapidly, so there was no chance for T2 decay, because we just did it in like 50 microseconds or something like that, and T2 decay is like about 1/10 of a second. So we just did a quick flip. Why is it the sine? Well, it's the sine because we want to know this distance right here. So we flip down that angle, and so here's a right angle here. So that's the opposite leg of the triangle. So this guy is basically the sine of the angle. So so that's why there's the sine there. So and so that's the amount. It's the amount of transverse magnetization, because here's transverse magnetization that we're interested in, because remember, you can't record the Z component. The Z component is invisible because it changes so slowly. It changes very slowly. So that's an important thing to keep in mind. So you're only recording the transverse component. So the sine of the flip angle tells you how much transverse component you start with, which is proportional to how much signal you have. Okay, so that's the very first thing, and then what we're going to do is we have to take an integral, which is just a sum, across all frequencies. So the idea is sum across all different frequencies that might be occurring in the sample. And what are we summing? So what we're summing is this funny symbol, which is a function of frequency. So what this is, it's what are the different frequencies? So this is, we'll call this the spectral density function. So it's just some function that says you have such and such of this frequency and such. You have to say more of this frequency, less of that frequency, none of this frequency. So it's some kind of function that just describes what the distribution of frequencies in the signal is. and so it's a function of frequency. So it's a graph basically. It just has frequency on the x-axis. Okay, so that's the spectral density function, and then that's multiplied by the T2 decay. So the T2 decay, because here's a function of time. This says how does the signal change across time, and so T2 decays across time. But we also have to consider that T2 itself is actually going to be a function of frequency. So there'll be different decays for different frequencies. So the T2 at each little spot in the brain is different. And then finally, there's the rapidly rotating component. So remember, this guy is, this is the rapid oscillations. You see, these are the 123 million rapid, rotations in transverse plane. In the XY transverse, XY. So those are the rapid rotations as a function of time, because that's time. That's the same time here. So when you look at these equations, one thing always to keep in mind is look at sort of like, so there's a t here, and if you look across the equation, there's a t here, and there's a t here. So this equation is a function of time. So that's how time sort of gets into this signal. So this is our complex val recorded signal. But then the other thing to look at is what we're summing across. So we're summing across frequency. So here's frequency. So we're summing across frequency. There's frequency there, and then last but not least, we have for each small increment in frequency. So that's our. So there's frequency up there, and there's frequency. So when you look at the equation, just don't sort of you have to actually sort of fixate each part of the equation and keep in mind what's doing what. So here we've got, for a moment in time, these two things are dependent on time. This one's not dependent on time, but this is the one that we're summing across in order to sum up this whole mess for each frequency to make our signal. So what this describes is what kind of a signal you would get for some arbitrary distribution of simultaneous frequencies that are added to each other. And so now what we want to do is try to solve this integral for some kind of realistic distribution of frequencies. So this, again, it's not a very specified equation. It says this is some spectral density function. We don't know what it is. Could be anything. And so what do you do in this situation like this? One of the things you do in a situation like this is, let's just make one up. So at first you might think this is like the spherical cow. So instead of saying should we try to measure it? Maybe it's some arbitrary thing. We don't know what it is. Instead of that, let's just say, let's just make one up that's kind of a reasonable cartoon of a kind of distribution of frequencies that you might get. And then let's solve that, and then see what that does, and then we can say okay, the real distribution of frequencies isn't quite like that real one, but it's kind of close, and this is an approximation of it. So that's the strategy for today. So we have this equation that just says your signal is going to be the sum of all these different oscillating protons that are oscillating at all these different frequencies. We add them all up. They're decaying in time, and then we get our signal over time. So now we have to just make up make up an equation. So the equation will make up, so here's the equation we'll make up. So this is an equation for how the frequencies are distributed. And this thing is called a Lorentzian inhomogeneity or Lorentzian distribution. Inhomogeneity or distribution. So what does our Lorentzian distribution look like? So I did have a couple of years ago I had the sign in the equation wrong for about a year, but I fixed that. So our Lorentzian distribution is just equal to whatever it's scaled by our starting magnetization. So our starting magnetization, and then it's got the gyromagnetic ratio times some measure of the width of this, the width of the distribution. So the kind of distribution we're going to look at is something that sort of goes like this, kind of like a Gaussian distribution. So there's a lot of these frequencies, so this is frequency. There's a lot of these frequencies, and then you fall off to almost nothing. So that's what the equation that we're going to make. It's not a Gaussian, but it's a slightly different equation. So what is this thing in the equation here? Well, if you look at this, if you remember our original equation, our original very first equation was the resonant frequency equals the gyromagnetic ratio times the B field. So that's the same thing here. So this is the gyromagnetic ratio times the frequency, except it's just, instead of the full frequency, it's just a frequency width. It's just something like this. And so that thing is a frequency. That's basically a frequency, because we want, we want to find out like how much of each frequency is there. So that thing is actually a frequency. So that thing is in the numerator squared, and then in the denominator we got that thing again. Squared again, and plus our variable. And so the variable is this particular frequency, and we're subtracting off the center frequency. So that's our Lorentzian distribution. So again, look at this. There's one. This is this W. This is, so omega 0 is the center frequency. This is that's the transmitter frequency. This guy is the variable. So this guy is the variable over here. This guy's a variable. That's the only variable. This guy's a constant. This whole thing is a constant. That whole thing is a constant. So you basically have sort of constant over constant plus something squared. So I looked at the square. And so that's the basic equation. So the basic equation, if you just want to plot it in MATLAB, you would plot something like, say, y equals some constant over another constant plus something squared. Because this omega 0 is a constant also. So after you subtract it off, you just square it. You just have, so this is the equation we're looking at. And if you plot an equation like that, what does it look like? So it will basically look like something like this. So this will be the center frequency. And you'll get an equation that sort of looks just like, kind of like a Gaussian, but a little slightly different shape than a Gaussian. And again, just plotting this equation, if you plot this equation what you get is you basically get 1 over here at the peak when you're on the center frequency. So why do you get 1? Well, again, you have to operate the equations to sort of get a feel for how they work. So if we're at the center frequency, then omega minus omega 0 is 0. And so then you just have this thing squared over that thing squared. And so that's 1. But then we multiply by mz 0. So this basically is, mz 0. It's 1 before we multiplied by it. Now, the width here then is proportional to the delta B0. So what that means is if we change delta B0, it'll change the width. And how would it change the width? So if we make delta B0 bigger, a bigger band of frequencies, we'll get something that sort of looks like this. It'll still go up to the same point. So this is, delta B0 up. So if we make delta B0 bigger, it'll just widen out the distribution. So notice what that means. It means there's more frequencies in, there's more area under the curve. So that will be important later. So more area under the curve, more frequencies. So this is basically what this is. This is our spherical cow. It's just a fake distribution of frequencies, a convenient fake distribution of frequencies. And so what we're looking at here is now if we just take that fake distribution of frequencies and just substitute it in here and then just try to solve the equation, solve this integral here and just see what we get. And so what we could do to start with is we could just say, what if we only had one frequency? So what if we just had just like an extremely small delta B0 that just gave us one little spiky single frequency? What would we get? What would we get for our solution? And so the solution in that case is going to be, I'll draw it down and erase it. So the solution in that case is going to be very simple. There's only one frequency there. And so it's just basically going to be, mz0 sine of the flip angle, and then however much T2 decay we've had, and a single frequency. So minus I omega t, something like that. And it's the center frequency. So say that we just have a single center frequency. So that's not surprising. We know that when we take a derivative or integrate these e functions, we get another e function. We get another exponential function. And so it turns out it looks very similar to what we started after we take the integral. And that's not surprising. It's just got one frequency. It's decaying by T2. And it depends on the flip angle, and it depends on how much starting magnetization you had as to give you your signal. But that's kind of a boring one, because you could have predicted, you didn't need the equation to do that. You just had one frequency, and we know what the signal is going to be if there's one frequency. So we'll erase that one, but we'll solve it for the more general case of where you have this kind of setup where we've got a distribution of frequencies that looks like this Lorentzian distribution. So in that case, what we get a little more complicated thing. I'll draw it twice so that we can sort of like consider the effect of T2 star. So here's our signal. So the first thing is pi. So where did pi come from? So pi came from when we integrate something like that. So we'll just leave it at that. You end up getting a pi. So then we're multiplying by the, hold on, let me just get another blue one, because ooh, sorry, could I get another blue?
Oh yeah, I'll bring it out to you.
Okay, thanks much. Keep my color scheme consistent. So here's our MZ0. That just came from this guy. And then we're multiplying by the sine. That was another constant. That didn't change. So we got the sine of the flip angle, just like we had before. Okay, so now we have the first thing here, which is different. So we have e to the minus t, but then we're going to be multiplied by this delta b 0. So when you first look at this, if you're ready, sort of like from our first oh, excellent new blue. Oh man, a powerful brand new blue. Okay, so we got this thing. Let me just finish the equation before we start annotating it. So we got this one, and this one is a function of how wide the frequency range is. And then we've got the T2 decay. That didn't change. That would look like the original one before we took the integral. So there's minus t over T2, regular T2. That's all good. And then this one didn't change. When we take the integral of that, aside from like that one basically doesn't change either. So, and that's one frequency. That's the starting frequency. So this is our when we take the integral, this is the result we get. So we get we basically get pi is a constant, mz0 is a constant, sine of alpha is a constant, a certain amount of decay due to the width of the frequencies, and a certain amount of decay due to T2 decay. We'll sort of say what the difference between these two are. This is the star part of the T2, and this is the T2. And then we got the fast oscillations. So let's just sort of see where these things came from. So this one came from here. So that's a constant. So what is the result? When you first look at this, it's kind of weird. So I got one frequency in it. So that's kind of weird. Like it's just the magic of this particular distribution, and the magic of sort of adding up a bunch of different frequencies. We just end up with one frequency. So this guy is this is the rapid oscillations part. These are the oscillations, but they're oscillating at one frequency, the center frequency. So we just have the center frequency. So the signal we're going to get out only has one frequency in it. And then it's decaying away. So this is T2 decay. It's decaying away, and then it's also decaying away here. So this one is extra decay. That's extra decay because remember e to the minus t, where t is 0, time equals 0 is 1. So anything beyond, as soon as t goes above 0, this guy here just gets less than 1. And so it's more decay as a function of time that is proportional to how much range of frequencies you have in there. So if you have a larger range of frequencies, you have more decay at a later point in time. Now, when you look at this, it's kind of like, well, that one's in the numerator, the T2 is in the denominator. So typically, you would you would write out, if you wanted to think of it like a time, I mean, you can see that if you increase the value here of this exponent, you could just try it in MATLAB. If you increase the value of this exponent, what's going to happen is the decay will be more rapid with time. But time constants are down in the denominator. Why are they in the denominator? Well, if you have a larger time constant, that means less decay. So just remember that. So like if your time constant is longer in time, that means that there's going to be less decay. If your time constant is smaller, that means more decay. So it's the inverse of this guy. So sometimes you might want to write this guy. We could write this guy as 1 over t2 prime. So we could think of that person, this actor, as a time constant. If you're thinking of it as a time constant, then it's going to have to be 1 over it. But you can see here we've written it in the numerator of the exponent, and here it just means if you increase this, you get more decay. So that's one thing to keep in mind, because the time constants are always going to be sort of inverted from the numerator. Okay, so this is just the flip. This is a constant. This is, your starting magnetization. Okay, so now what do you typically do? What we typically do is combine these two. So that because we can't easily get them apart in a way. So if we write out our final free induction decay equation, we get our signal is equal to pi times mz0 times the however much flip we did times a decay term, which is minus t over t2 star, times our single frequency, minus I omega 0 t. So that's just the center frequency. So this basically is just a sinusoid at the center frequency at 123 megahertz. It's decayed by T2 star, which includes sort of regular T2 plus this additional decay from the range of frequencies, and then these are constants here. So that's our final solution. So now we have to sort of like try to sort of understand, what does that look like? And in particular, let's try. So what is the T2? What does the T2 star equal? Well, it's 1 over T2 star is just equal to 1 over T2 plus 1 over T2 prime. That came from this guy. And if you look at that, you can also just look at it from the point of view if you have two things raised to a power multiplied by each other, and you know from algebra that one way of rewriting this is just e to this thing plus this thing, just adding the exponents is the same as multiplying two things with separate exponents. And so we're just adding the exponents, and we converted this gyromagnetic ratio times the width business into a time constant by taking 1 over it. And so that's it's a little confusing when you see it written out the first time, but that's where the T2 star time constant comes from. So it comes from sort of considering the regular T2 decay and then adding in this additional decay that's due to the frequency spread. Okay, so what are these two things? So what does this extra decay mean? So before we talk about that one, let's just talk about the regular decay. So what is the regular decay? The regular decay is basically we call it unrecoverable. And it's due to basically just sort of jostling between all these different protons that are slightly getting out of phase with each other. So just imagine like they're like powerful little magnets, and they're all sort of like whipping around 123 million times a second, and they're just sitting in a forest of other magnets. And all those magnets are sort of like, they're all sort of going in slightly different directions. They're being wiggled around because, they're not at absolute zero. They're like at, body temperature. And so all the atoms are wiggling a little bit, so the magnets are sort of like rotating around while they're wiggling. And so it's just like this just crazy mass of magnetic fields, from all these different weird spatial distributions of atoms in your brain. That's what's causing the T2, is just all these kind of interactions between these very rapidly precessing protons. So this is, intrinsic. It's an intrinsic decay in the coherence of the magnetization. So it's what happens is when these magnets interact with each other is they slightly slow down or speed up, and they essentially start to get out of phase with each other. And as they get out of phase, when you add them all up, when you do your vector sum for the RF coil, you get a smaller and smaller signal. So this is, unrecoverable, intrinsic, rapid oscillations. That's T2. So what is the star part of T2? It's not T2 star, because T2 star means like, T2 plus this other stuff. So it's like T2, T2 prime. What is this? These are the recoverable ones. So we'll see why are they recoverable. So these guys are recoverable. And they're also called static. So we'll see. Static. It's a gradation of staticness, because static could mean it doesn't change very much in the 20th of a second. That's the version of static that we're talking about. These things are rapid. That's 123 million changes per second. That's very rapid. So something that only changes in 100th of a second is static relative to that. So we'll put that in quotes. So static. So that's what we mean by static. These are rapid, really rapid. Okay. So these are static or recoverable. And so what causes this? So let's just sort of go back to, why did we come up with a distribution like that? Well, it's partly what the distribution looks like. So if you just take you could just take a sample of a chemical, stick it in a simple chemical, not a brain, just a simple chemical, stick it in the NMR machine, get a spectrum of frequencies that come off it, and you'll see something like that. So that means something has gone wrong, because we know from our original equation that the frequency of precession equals gyromagnetic ratio times B0. That's it. So if B0 is the same, then the frequency should just be a spike. There should just be one frequency. So the question is, why do we have this? Something must have gone wrong. And what went wrong? Well, the B0 is slightly disturbed in different parts of the sample, and this occurs even with just like you could just stick a little blob of chemical into the NMR machine. You still get something like this. It's disturbed. It disturbs the uniformity of the magnetic field when you stick something into it, and so that's what's causing it. So this is that static sort of addition to the magnetic field. But it's a big effect. So if you actually graph, if we actually graph what it looks like, let me just make this guy go over here so I can make a nice graph. So here's recoverable. We haven't said how to recover it yet, but that one's recoverable or static. So what does it look like if we plot out like T2 decay? So if we just go and, plot out a graph with time, this equation, so here's time, and this is our signal. It's a vector quantity, so let's take the length of it. So that means, like, let's just get the amplitude of the signal. We'll ignore the phase of the signal, what direction the complex vector is pointing. We'll just say how long is the vector. And so if we plot that out, what we get, if we plot out T2, it's going to start at mz, well, it won't be mz0, it'll be, mxy0, our starting transverse magnetization, whatever it is. And then it will make a nice, exponential decay like that. So that'll be our e to the minus t over t2 curve. So what does this curve look like when it's got the t2 star in it? It's much more rapid. It comes down something like this. So this guy is e to the minus t over t2 star. So t2 star is a big effect. When you make this, when you make it into a star, there's a huge hit. And so what's the implication? Well, the implication is that there's a bunch of magnetization still left in there, but this other distribution of static offsets is messing it up. So there's some hidden magnetization that's still there, but it's been sort of messed up by having the magnetic field, the B0 field at different points in the sample being slightly off from each other. And so we can get it back. So that's the implication. So what do these things actually look like? So if we plotted that whole equation, it's got the rapid oscillations in it. So this equation, if our distribution of frequencies is equal to one of our Lorentzian distributions like this, nice well-behaved one like this guy, what does the signal look like? Well, the signal, it just looks like a gazillion oscillations, 123 megahertz, sort of falling off like a perfect exponential fall off. Like that. Yeah, get them all straightened up. Now, what if, and it doesn't get bigger, it just keeps getting smaller. So now the question is, what if we don't have something that's like that? So let's take another very simple example. Like, what if we had something that was narrower than that, and where it was something more like this, where it was more like, here's the center frequency. It was more like sort of like a little spike like that. Then we would get something that wouldn't be described by this equation anymore. It might look like something, it would start off and then it would get a little smaller and then maybe get a little bigger and smaller, a little bigger and smaller, something like that. So it would kind of have like a little bit of a wobbly look to it like that. And if you stick a chemical sample in there, you'll see something like that. And so this one, it's more or less exponential. So I mean, you could approximate that pretty well, with our exponent. It's still got an exponential look to it. So this guy would be, e to the minus t over t2 star. That basically is basically this thing. But because our distribution of frequencies wasn't like this perfect Lorentzian, it will look like something else. And in real life, this curve could actually sort of go like this. Might be a little bump over there. Might be a little asymmetrical. There's a whole bunch of slightly different shapes that it could be. And then those are harder to figure out what exactly this signal equation would decay. So what you should think of T2 star as is it's basically just, it's like an idealization if we had this kind of a distribution, then we're going to get a very simple equation like this, and so T2 star will just be sort of an approximation of something, of any kind of distribution of frequencies that sort of looks like this. So it's not the real one. So whenever we're doing this and sort of using a fall off like T2 star to calculate something, we're doing an approximation. We're just saying, well, we think, the distributions, they're almost always spiky like this, and this is sort of a good approximation, but it's not the real thing. The real thing is, what you would get if you tried to integrate. You'd have to numerically integrate this equation with some random, nasty-looking distribution that doesn't look like this nice, well-behaved one. And then you could calculate this. That's how you would calculate this slightly wavy curve if you stuck in a little spike for our distribution of frequencies. So in the last 1 minute, we'll talk about this a lot more. Does this occur in the brain? Yes, it occurs all over the place in the brain. So one place it occurs is where the magnetic field is all messed up is right around the nose, because basically that's right where the olfactory bulbs come out, and the olfactory epithelium is right there, and there's a bunch of air very close to the brain. So this is air. And there's also there's a little tube in your ear that goes very close to the brain. It's like a little tube of air that goes under the brain. That's another area and so what will happen is you get some distortion around there. It'll move the image for reasons we haven't explained yet. And the same thing will happen here. It depends on what direction. It'll massively sort of distort this part of the image right here and distort this part of the image. Because of this kind of problem. It's a static disturbance in the magnetic field. And it's going to really mess up our signal if we're relying on a T2 star decay, which we often are. But, the bold effect, which we'll talk about later, blood oxygenation effect, that's a T2 star effect. So we're trying to we have to have a pulse sequence that gives us T2 star. So it gives us the same thing that causes the distortion. So we're kind of stuck between a rock and a hard place. We want this effect from the effect on the magnetic field of the oxygenation, because we need that. We need this effect here, the frequency offset from oxygenation, but unfortunately that messes up our image. So we'll sort of go over ways we can try to fix that without killing our signal, because we still want to, have our signal. Okay, so that was way too rapid over the last part, but we'll talk about the bold effect and image distortions in great detail later. So we'll end the recording now, David, if that's okay.